Hello dear students, today we will see experiment number 1 of your DSP lab, that is a digital signal processing lab. The first experiment is the sampling theorem. Here we need to verify the sampling theorem for the three following cases, that is the oversampling, exact sampling and undersampling. Before this we'll see what is a sampling theorem. A continuous time band limited signal can be represented by its samples and can be recovered from its samples provided the sampling frequency should be greater than or equal to 2 times the maximum frequency. Okay, and this condition it is referred to as the Nyquist criterion. Fine, or you can tell this as Nyquist rate also. Nyquist rate is nothing but the sampling frequency should be greater than or equal to 2 times the maximum frequency. And why we need this Nyquist rate? Because while doing the reconstruction of the signal, that is we want the analog signal after the digitization process, we want to reconstruct the signal exactly as we have given the input. So for that you need to follow this rate, that is Fs should be greater than or equal to F maximum. Okay, now starting with the program, first three commands will be same, that is the CLC, clear all and the close all. So CLC is nothing but the it is the command which clears all the text from the command window. Then clear all is it will clear all the previous data in the software, and close all is it will close all the windows with respect to the MATLAB. Okay, now here always you have to end again all the commands with a semicolon in MATLAB. Now you need to plot a signal, and it can be a sine wave, it can be a cos wave, or it can be two sine waves, or it can be two cos waves. Now we will plot a composite wave, that is the combination of two cos waves. Okay, so if we add any two cosine waves or two sine waves, it always results in a random wave. Okay, it will result in a random wave, and as it is a cosine wave, it will always start from the maximum value, like here, no, this here it is starting from the maximum value. This is the combination of two cosine waves, because we have taken two cosine waves and we are adding up this, so we get here the composite wave which will start from the maximum value. Okay, then now we will write the parameters required for plotting the original signal. So still we have not gone to the sampling process. Still we are plotting the original signal or the wave. So for any wave we use the frequency, or we require the frequency. First we will consider the frequency for the first wave as 1000 Hertz. That is F1 is equal to 1000 Hertz, or it is 1 kilohertz. And second wave will take second wave frequency is F2, which will be 1900 Hertz, that is equal to 1.9 kilohertz. Now after this, for sampling frequency we need the maximum frequency of the considered wave. So for that we have to take the maximum frequency of the two waves which we have considered, that is we have to take the maximum of these two frequencies. For that we are using the command F max is equal to maximum of F1 and F2, that is F max is equal to max of F1 and F1 comma F2. So this will give you the maximum frequency component of the signal. After that for every wave we will have, or we have to take the time period. We will indicate this by capital T. So here capital T, it is nothing but the reciprocal of the frequency. So here we will take capital T as 1 divided by minimum of F1 comma F2, which is nothing but the time index or the time period. Okay, sorry, that is nothing but the time period or the signal period that should cover the entire length. Now next we need to define the time axis, that is the time index. For that we will take this command. Okay, that is T is equal to 0 colon 0.01 multiplied by capital T colon 2 star T. Now what is this first parameter in this. The first parameter is the starting, that is the start of the axis. It will start from 0. Okay, it will start from 0, then colon. After that, you need to decide the scaling factor. So for that, we have taken 0.01 multiplied by capital T. Then this 2 star is the uh, uh, ending of the time axis. Okay, it starts at 0, it ends at 2t, and the interval or the steps which we are taking is 0.01 into t. Okay, so now we have decided all the signal parameters. Next is we have to generate the original signal and we have to plot it. To generate the original signal, here we have taken the two cos waves. So here now the composite signal or the signal which we want to plot, it is given by x is equal to cos of 2 pi t f1, that is 2 into pi into small t into f1 plus cos into 2 in cos of 2 into pi into t into f2. So here this is the first signal, this is the this is the first cos wave, this is the second cos wave, and we are getting a composite signal by adding these two, that will be equal to x. Now we want to plot total 4 signals. So we have to take a quadrant which or a window which will be having 2 rows and 2 columns. So here I have taken subplot 2 comma 2 comma 1. This first parameter is the rows, number of rows is equal to 2. Second parameter is the column, number of columns is equal to 2, and we want to plot our signal into first quadrant. So I have placed here 1. After that, you have to use plot t comma x. So here t is nothing but the time, and x is the amplitude of the original wave. Now next here we have taken the grid on. Okay, so here we have taken grid on. Grid on means here these lines you can see, no, this light shaded lines, these are nothing but the grids. To on that we can write this command as grid on. Okay, now after that we want to give the title for this graph, so we will write it as title continuous signal. Then we want to label the x-axis, x label in inverted commas t, that is the time, and y label in inverted commas, the amplitude is x of t. Okay, so this is nothing but the plotting of the signal. Now after this we will check for the conditions, that is the first we'll go for oversampling. Okay, so in oversampling the frequency of the signal, that is the sampling frequency, it should be greater than 2 times the maximum frequency. Okay, oversampling is what? The sampling frequency should be greater than 2 times the maximum frequency. So here we have taken fs1, that is the first frequency, as 10 times the maximum frequency. So I have taken here a scaling factor 10. It means that it is 2 times greater than that of the maximum frequency. Yes, no, 10 is greater than 2. So we want the condition which should satisfy this one, that is fs should be greater than 2f. I have taken it as 10, therefore obviously it is greater than 2. Okay, so the first condition is oversampling. Now next here we will decide the what time index. So n1 is equal to 0, it is starting from 0. Then we will take steps of 1 divided by fs1. Okay, that is the frequency fs1 colon 2 star t, that is 2 into t. It starts from 0, it ends at 2t. So this is nothing but the time scale. Now next we want to have the first signal, our signal, that is x1. Okay, it is cos of 2 pi f1 n1 plus cos of 2 pi f2 n2. Oh, n1, sorry, n1. Okay, Here n1 we have decided, no? So it is n1. Okay. Now next you have to subplot this again. Subplot 2 rows, 2 columns. We want to plot or we want to display our signal in the second quadrant. So 2. Okay. Now here we have taken stem 1. Okay. We have taken stem n1 comma x1. Why stem we have taken? Here stem is a command which is used to get the discrete wave. Okay. And plot is a command which is used to get a continuous wave. Now we want to show the discrete values here in the of the signal. Therefore, we have used the stem command. Okay, stem bracket n1 comma x1. Now we want to hold this value. That is, we want to hold this discrete values. So we have used hold on command. Okay. After that, we have to plot this. Fine. We have to plot this. Plot n1 comma x1. Okay. Now I want my continuous signal. See here it was stem n1 comma x1. It is for the discrete wave. That is, this blue lines is there, no? This is the discrete wave. So for that we are using stem n1 comma x1. Now I want the continuous wave also. So for that I am using plot. Okay, plot n1 comma x1. I can write only n1 comma x1 also, but here I have added an extra color to the continuous wave, that is red. You can add any other colors also. There are many colors, blue, red, then you have yellow, green. Okay, I have used here red. If you want to use green, you can type it here as G. Fine. So I want to make a difference between the discrete values and the continuous wave. So for the continuous wave, I have taken it as R. This plot, it will it will give you a continuous signal. Fine. Now next again grid on. These lines are there, no? These blocks. Okay. This is nothing but the grids. These are nothing but the grids. Now again we want to hold on this because again you'll be getting some other figure window. So we don't want that to overwrite this one. Okay, this window, this figure. So we are using the command hold on. Now we want to give a title to this figure. So for that title, oversampling condition. Okay, that is fs is equal to 10 times f. We have taken the sampling frequency is equal to 10 times the maximum frequency. Okay. Then next x label here we have taken it as n. Why n? Because we were showing the discrete values here. Previously we have taken as t in the continuous signal. There it was time. Now here we want to display the discrete values. So here I have taken it as n. And y label, it is the amplitude, that is x of n. Okay, this one. So we are done with the oversampling condition. Now next comes the exact sampling condition. Okay, exact sampling. Exact sampling is what? The sampling frequency should be equal to twice the maximum frequency. It should be equal to. Oversampling was greater than. This should be equal to. Exact sampling is equal to. Okay. So here we have taken fs2. fs2 is equal to 2 times the maximum frequency. Okay. This is for your exact sampling. Okay. Condition for the exact sampling is sampling frequency should be equal to 2 times the maximum frequency. Now we have to define the time scale. For that we will take it as n2 0:1 by fs2, that is this frequency, and colon 2 times the time period, that is t. Okay. Next we want our composite signal to be plotted for the exact sampling condition. So for that we'll take it as x2 cos of 2 pi f1 into n2. This is n2, that is the time scale we have decided here. Then plus cos of 2 pi f2 into n2. Okay. Then again we need to plot this. We want our exact sampling figure in the third quadrant. So 2 columns, two rows, two columns, and the figure in the third quadrant. Now we want the like discrete values. Okay, so for that we are using stem n2 comma x2, and we want this to be displayed, so we'll use the hold on condition so that it does not get wiped off. Okay, so hold on, then after that you need to plot this. Okay, we want the plotting of the continuous wave. So for continuous signal we are using plot, for discrete wave we are using stem. Plot n2 comma x2 because we want to differentiate these two by using different colors. So by default here we are not using any color. By default it will be blue. These lines are there, no, these are the discrete values, blue lines, and the red one is the continuous wave. For displaying the continuous wave we are using the red color. Then again we will use the grid on, that is these grids will be on. It will display the grids. Okay, these are there, no, square boxes, these are nothing but the grids. Now again next it is hold on. Okay, again we want to hold on so that it does not get overwritten, so we are using the hold on command. Then we want to give a title for this. This figure is for the exact sampling condition, and the condition is fs should be equal to 2 times the maximum frequency. Then x label, these are the discrete values, blue lines are the discrete values, therefore we want to label the x-axis as n, that is for the discrete values. Then y label, here y label is there, that is x of n, that is the amplitude. Okay, so here this is our second condition, that is the what, exact sampling. Okay, then next you have, next is the undersampling. Okay, just a minute. Undersampling condition is what? Your frequency, whatever you are taking, it should be less than twice the maximum frequency. Okay, it should be less, it should not be equal, it should be less, it should be less than that of your maximum frequency. So you have to take the scaling factor less than 2. Here the scaling factor is 2, no, you have to take the scaling factor for f maximum, which should be less than 2. So here we have taken fs3 is equal to 1.2 multiplied by the maximum frequency. Yes, no, 1.2 is less than 2, so undersampling is, it should be less than twice the maximum frequency. You can take any value, you can take 0.8, you can take 1, okay, you can take 1.8, 1.5, like that you can take. Now fs3 is 1.2 multiplied by the maximum frequency. So here next is we have to decide the time scale. So time scale n3 is equal to 0, is to, not is to, it is colon 1 divided by fs3, that is the frequency we have taken, 1 by fs3 colon 2 times t. Okay, this is the time scale. Then we want our signal x3. Okay, that is for the undersampling condition. x3 is equal to cos of 2 pi f1 n3 plus cos of 2 pi f2 n3. Okay, so here what happens? Our signal will be sampled. Okay, next we want to plot our signal. Okay, so here to plot our signal, what we will use? We will use subplot 2 comma 2 comma 4. Already in the 3 quadrants we have displayed, we have used the quadrants. Okay, 3 quadrants we have used. First quadrant is for the displaying the continuous signal, that is the composite wave. Then second is for the oversampling, and third is for the exact sampling, and fourth quadrant we are using for undersampling. Next we want to display the discrete values. So for that we are using the stem command n3 comma x3. Now we want to hold on this so that it does not get overwritten. Then we'll use the plot signal, plot command. Okay, this plot command we are writing it as n3 comma x3 comma r. Again, we want to differentiate the digitized value, that is a discrete value, and the continuous signal. So for this discrete values, I'm not using any color. By default it will take blue color, and for plotting the continuous signal, here I'm using red color. So this red color is the continuous signal. Then grid on, again you want to on the grid, then you have hold on. Okay, after that you will write the title. This is for the undersampling condition, that is fs is equal to 1.2 f, or you can write it as fs is less than or equal to less than 2 f. Okay, then x label, it is n, x axis label is n, y axis label is x of n. Okay, if you x of n, now this is the output what we get. Okay, in the first quadrant we are getting our continuous signal, which is a composite signal, which is obtained by combining two cosine waves of different frequencies. Okay, this first. And in the second quadrant, this figure is for the oversampling condition, where your sampling frequency, it is greater than 2 times the maximum frequency. Okay, here you get more number of samples. Fine. In oversampling you get more number of samples. Okay, and this is for oversampling, no? So you are getting more number of samples, not at the maximum peak. Okay, you will not get more number of samples at the maximum peak, but you will get some more number of samples here, like this. Okay, at these corners you will be having more number of samples, and this oversampling, it requires more bandwidth. Okay, and this oversampling, it can be used for communication, and there will be no loss of data when you are using the oversampling condition, and it cannot reconstruct the original signal. Oversampling, whenever you are using oversampling, it cannot reconstruct the original signal. Next is the exact sampling. See here, in the third quadrant you have exact sampling. Okay, exact sampling, it is having somewhat less discrete values, that is here blue lines are less, no, as compared to the oversampling condition. Okay, and these discrete values are at the peaks of the continuous signal. Here you can see these are at the peaks. And the last figure, it is the undersampling condition. Okay, now undersampling condition, it is having less samples. See, this is having more samples, whereas this is having somewhat less samples than that of the oversampling. Whereas undersampling, it is having very less number of samples as compared to these two. Fine. And here this undersampling condition, it is not preferred for communication. Okay, this is not preferred for communication, and because you cannot reconstruct the signal here. So this is about the explanation of the three conditions for verification of the sampling theorem, that is the oversampling, undersampling, and the exact sampling. Now we will see the program. So I will copy the program from here. This is the executed one. You will get I will open MATLAB software. I will use program from here. DSP programs. Okay, I'll start from here. These programs are there in the manual. All the programs are executed and tested, which you have in your manual. So you can write it from the manual, the programs. So here already I have copied and pasted here the signal. Just I will show you. Same thing, same procedure you have to repeat. That is, you have to open a new script, and in new script you have to write your program in the editor window. After that, you have to save the program with a name with extension .yum. Okay, in MATLAB all the programs are saved with the extension .yum. Then you have to save the program. After that, we will run the program. Okay, so here we will run the program. It is asking for changing the folder. So this is a output what you get. Okay, so you are getting the continuous signal, which is a composite signal. This is the oversampling condition where the sampling frequency is equal to, or it is greater than, it is greater than, not equal to, it is greater than 2 times the maximum frequency. So we have taken it as 10f, and here this is for the exact sampling, where the sampling frequency is equal to 2 times the maximum frequency, and this is the undersampling where your sampling frequency is less than that of the 2 times of maximum frequency. So here the scaling factor, instead of 2 we have used it as 1.2. You can see the differences here. Here you are getting more number of samples in the oversampling condition, whereas in exact sampling you get the samples at the peak value. Okay, here you are getting the samples at the peak value, and the samples are the number of samples are less than that of the oversampling. Then in undersampling also you are getting the samples at peak value itself, but the number of samples are less than that of the exact sampling. Okay, these are the 4 figures which you have plotted in a single figure window by taking 2 rows, 2 columns. This is the first quadrant, second quadrant, third quadrant, and the fourth quadrant. Okay, so this is your first experiment which you have to do in your DSP lab.